all of the tube circuits that we've built up to now have essentially been digital circuits. So what this means is that we're driving the grid of the vacuum tube high enough or low enough to drive the tube into cutoff or saturation to give us essentially a logic low and a logic high output. But what I want to do today is a little different. I want to maybe go off on a little tangent here and take a look at an analog circuit. And quite possibly one of the most important analog devices out there is the operational amplifier, or an OpAmp. Now, vacuum tube op-amps weren't all that common, but there was a couple built. There was the K2W, and that's been kind of my primary inspiration. Now, this op-amp is wild because it requires insane voltage, plus 300 volts to minus 300 volts. So that means that you need a total of 600 volts across this component. And that's a lot of voltage, and it terrifies me. But there is a fantastic video out there about the K2W op-amp, and that's by Mr. Carlson's lab. And he actually fires up 600 volts of power supply and gets this thing operating. But I'm not as brave as Mr. Carlson. I'm also not nearly as smart as Mr. Carlson. So what I want to do is try and rebuild that op-amp, only at a much lower voltage. Essentially 24 volts on the plate and minus 12 volts for our bias. Now, this seems kind of crazy because that had 600 volts to operate correctly, and I'm like at, not even 10% of that. So this is insane, but I have some ideas about how it might work. So everything else we've been doing is at 24 volts and minus 12 volts, and I would really love to use those voltages. So let's hop over to the bench and we'll first take a look at what an op-amp is, and I'll do my best to explain it. And then we'll take a look at the K2W schematic, and then maybe try and figure out how we're going to build a low voltage version from there. So let's hop over there and get started. So what is an op-amp, or an operational amplifier? And full disclosure right off the bat, I'm probably the worst person to explain this. There's a ton of fantastic educational videos out there explaining op-amps. So I'll just give a quick rundown of my basic and limited understanding of op-amps, and we'll essentially just go from there. So this is the signal for an op-amp, and we have two inputs. We have a non-inverting input and an inverting input, and then we have an output. And the op-amp itself is, well, just an amplifier, and it has, generally it has a massive gain, like 10,000 or 50,000 or a huge amount of gain. But what sets this apart from just a regular amplifier is that it's amplifying the difference in potential between the two inputs. So if we have 1 volt coming into the non-inverting input and 1 volt coming into the inverting input, there is no difference between them, and so there's no amplification. So we'll get 0 volts out of our output here. But if we have, say, 1 volt coming into this and 0.9 volts coming into this, that 0.1 volt difference is going to be multiplied by the gain inside the op-amp, and that's what we'll see on the output. So that 0.1 volt is multiplied by, whatever the gain is, 10,000 or 50,000. So we get the output trying to drive pretty much as high as it can possibly drive. And conversely, if we flip that, if we have 1 volt into here and 0.9 volts into here, it's going to drive in the other direction, all the way down to a negative voltage. And so this operation is what they call open loop operation, and this is essentially a comparator. It's comparing the two inputs and giving us an output based upon that. Now, an op-amp really wants some kind of feedback, but we're just going to take a look at open loop right now. And once we get the circuit built and start looking at how it's working on the breadboard, then we'll take a look at adding in some negative feedback and what that's going to do. But right now, what I want to do is I want to build just this, an open loop, essentially differential amplifier that has a large amount of gain. Now at 24 volts and negative 12 volts using vacuum tubes, I'm not expecting to get, a gain of 10,000 or whatever. I would be happy with like a gain of 10 or something like that. So we got to keep some of our expectations in check. But how are we going to go about building this with vacuum tubes? So the first step is to take a look at something that already exists. And it turns out that the K2W is an excellent example of a vacuum tube operational amplifier. But you can see that it uses insane voltage, so plus 300 volt DC and minus 300 volt DC. And it looks incredibly complicated and hard to understand. But after analyzing this for a little bit, I started to see some patterns. And this tube on the right, this 12AX7 here, looked to me like just a standard inverting amplifier. There's a lot of interesting feedback and control stuff going on down here, but I just ignored that. So we had a plate resistor coming in, and then we have the output coming off that plate resistor. And then it went through some mystery component here over to the grid. And then when it went to this grid, well, we have no plate resistor there, but we do have some cathode resistors to ground. And then we have our output coming off directly off of the cathode. Well, that's a cathode follower. And well, that makes sense. We need an amplifier to amplify the difference between the two input voltages. And then we need a cathode follower to ensure that we have a nice, strong output. Because op-amps, aside from being essentially differential amplifiers, have a few more characteristics that are really important. And the first is that there's no current going into or out of the inputs. Well, that's easy enough to obtain with vacuum tubes. That's kind of an inherent quality of vacuum tubes. The other is that the output needs to be low impedance. And so the best way to achieve that is with a cathode follower. So essentially the right half, what we have is an inverting amplifier and a cathode follower. Well, that's pretty easy to build, so we can just ignore that for now. And then we take a look at the left half here. And this one is really interesting, because you can see that we have a plate resistor coming into the right side triode, but we have no plate resistor coming into the left side triode. And then both of the cathodes are tied together with a resistor that then goes to minus 300 volts DC. So this is the differential amplifier, and I believe sometimes it's called a long-tailed pair. So let's take a look at this, but boil it down as simple as we possibly can and apply the voltages that we're going to be running, not minus 300 and plus 300. Let's do plus 24 and minus 12. So I've gone ahead and redrawn the long-tailed pair, the differential amplifier portion of it. And you can see it's incredibly simple once we boil it down to the most essential components here. So essentially we have two triodes. The left triode, the plate is connected directly to our plus B voltage, which is 24 volts here. The right triode, the plate goes through a 10,000 ohm resistor to plus B. And then the cathodes of both are tied together. And then they go to minus 12 volts through a 10,000 ohm resistor. And so at first glance, it's simple, but it's confusing to kind of understand what's going on. So how does this actually work? Well, I don't have enough time to explain how long-tailed pairs work in massive detail. And if I'm being honest, I couldn't explain it. They're right on that bitter edge of my ability to grasp. But here is how I am starting to wrap my head around it. And it's all about the potential of the cathode in relation to the potential of the grid. Since there's no resistor on our inverting input tube here, the plate is always at 24 volts. And so whatever voltage is coming into our grid, it's important to remember that the plate is always going to be at 24, but the cathode isn't always going to be at the same potential. And that's because the cathode is tied to the cathode of our non-inverting input tube over here. And since this tube has a 10,000 ohm plate resistor and a 10,000 ohm shared cathode resistor, the potential of the cathode can change in accordance with the input into our non-inverting input here. And so as we change the signal up and down on the non-inverting input here, the cathode potential moves up and down as well. And if this cathode potential is moving up and down, this cathode potential is moving up and down right along with it. So it's all about the relative potential of the cathode versus the grid in both of these tubes. But having a plate resistor on one and no plate resistor on the other changes pretty dramatically what that potential needs to be to allow electrons to flow or not between the two. Now that's the best explanation that I can give for it, because I fall squarely into that I don't know how it works, but I know that it works camp. And there's a lot of things in life that I fall into that category for, but I'm happy that it works, and so I really do want to try and build this up. And since this is just the differential amplifier portion of it, we essentially need to take this output and feed it into an amplifier and ultimately a cathode follower. And so that's what this schematic right here is. This is my low voltage operational amplifier schematic. And you can see I'm using pentodes instead of triodes because I'm going to build this out of 6AU6s instead of dual triodes. The only things that I've added that weren't on our previous schematic was that I put in these little 4.7K resistors into the grid, as well as a desensitizing cap on there as well. And that's not so much for what we're going to do today, but for future use and ensuring the ultimate application of this works correctly. Now our output comes out of that and goes through two relatively large resistors, 220,000 ohms and 122,000 ohms, into the grid of essentially an inverting amplifier. And so we do one amplifier stage, but in my personal testing and simulating, I found that one amplifier stage wasn't enough, so I went through another amplifier stage. Still wasn't quite happy, so I went through a third amplifier stage. So we've got 3 amplifier stages. And then the final stage here is just a cathode follower stage for our relatively low impedance output. So it's a fairly simple circuit. There's just quiet tube intensive, there's 6 tubes. But I want to go ahead and build this up on a breadboard and then maybe give it a test out. Maybe we'll put some potentiometers on the non-inverting and inverting inputs here to see how our output changes depending on the voltage levels of those potentiometers. And hopefully it'll all work. So let's pull the breadboard out and build this up right quick. Okay, that all went together pretty painlessly. I was really impressed with how easy it was to wire this up on the breadboard. I mean, it is a little tube intensive. And as for what the tubes are, these 2 tubes down here on the back right are the differential amplifier. And then we have our 1, 2, 3 amplifier stages, and then we have our cathode follower for the output. And then up here in the front right, I've got 2 potentiometers. And these potentiometers go from 24 volts to ground, and the center pin of the potentiometers go to the inverting and non-inverting input of our differential amplifier. So essentially they just go to the grids. And the value of these potentiometers, which is directly on the grids, is being displayed on my oscilloscope over here. It looks like one line, but that's because right now both potentiometers are set equally. So the 2 separate values are exactly the same, which puts them right dead square in the center of the oscilloscope. Now the output out of the cathode follower is hooked up to my voltmeter here, and you can see it's reading 23.7 volts. This is essentially our plate voltage, essentially 24 volts. And the reason that it's reading high is because we have 3 inverting amplifiers. So we have an odd number of inverters, which means that our output is going to be inverted of what we would normally think the output of the OpAmp should be. And I did this so that I could end up with a total of 6 tubes, which makes it a nice complete module to power the heaters in series. And so when the 2 inputs are equal, the output is going to be high. And then when those 2 inputs diverge, we're going to see this output drop. And the amount that this output drops in relation to the amount that the inputs have diverged is going to be our gain, because I have this set up in an open loop configuration. So it's just going to create as much gain as it possibly can. Right now I have the oscilloscope set up to 0.5 volts per division. So if I move one of these knobs up to a half of a volt of difference, and we look at how much the output has changed, that should be able to tell us what our gain is. So let's give that a shot. There we go. That's about a 0.5 volt change. Yeah, and you can see we dropped down to about 11.4 volts from the original 24 volts. So that's pretty good. And if we go the other direction here, at about 0.5 volts, now we're down to about 10.1 volts. All right, so we're looking at, for 0.5 volts, we're looking at about 12, 13, 14 volts, which means that if we have a 1 volt change on the input, then that's double the change on the input, so we should expect double the change on the output, should be 24 volts. So we'll say it's got a gain of about 24 to 25. That's actually pretty good. I'm actually pretty happy with that, except I was happy with that until I looked at the data sheet for the K2W here. And it actually lists the gain here in the bottom left, and it's 15,000. So yeah, a gain of 15,000 versus our gain of like 25 to 30. Yeah, so we didn't make the best op-amp in the world, but we've made an op-amp out of vacuum tubes, and they're running at an incredibly low voltage. Oh man. All right, well, it's not perfect, but it's actually good enough for what I want to do. But op-amps aren't ever really meant to be run in open loop configuration. They really want some type of feedback. And so that's what I want to test next. I want to build some feedback into this. And so I'm essentially just going to build up this circuit right here. So you can see that we have our op-amp here, and then we have feedback coming from the output back over to one of the inputs with a resistor. And then out of that same input, we have another resistor to our input here. And I'm just going to use my function generator to put a little sine wave into here. And then the relationship between this resistor and this resistor is what defines the gain that we see on the output here. So if this resistor is, say, 10,000 ohms and this resistor is 22,000 ohms or 33,000 ohms, we should see essentially 2 times the gain or 3 times the gain. So if we have a 1 volt peak-to-peak signal coming into here with a 33,000 ohm resistor up here, we should see 3 volts coming out here. And then I have a potentiometer here for the other input to kind of set the offset voltage so that the whole thing actually works, because most op-amps are designed to go from a positive voltage to a negative voltage. And actually the K2W is designed the same way. If we look at the specifications here, we can say the voltage range is minus 50 volts to plus 50 volts. But my output is only going from 24 volts to, if we just max that out, to 7.6 volts at full saturation. So we're not going to see any negative voltage. So I'll leave a potentiometer in there to adjust the offset so that we can get the output working correctly. So this seems to be fairly simple to set up. I already have one of the potentiometers in place, so I just need to change out these 2 resistors and add them in and see if we can get it working. So let's go ahead and give that a shot. All right, I think I have everything hooked up correctly. I've got my oscilloscope hooked up to the output from our cathode follower, as well as the input coming directly from my function generator here, which I haven't turned on yet. Now the resistor coming in from the function generator is 10,000 ohms, so this resistor is 10,000 ohms here, and then our feedback resistor is 22,000 ohms. So that should give us a gain of 2. So let's turn on the function generator and see what happens. All right. Okay, so the bottom waveform here is the output from our function generator that's being input into our op-amp. And then the waveform on the top here is the output coming out of the op-amp itself. And both channels are set to 1 volt per division. So we can see that the input coming from our function generator is about 0.5 volts from the bottom peak to the top peak. And you can see that the primary output is about 1 volt from the bottom peak to the top peak. It's not quite at 1 volt, it's a little bit less. So our gain is close, but not perfect. So this would actually probably be pretty terrible for like analog computing. But it does mean that the feedback is working correctly. So this is set up correctly as an op-amp with negative feedback. So let's change our 22,000 ohm resistor to a 33,000 ohm resistor and see if we can get more gain out of it. All right, so it changed from 22,000 ohms to 33,000 ohms, gave us a little more gain, but not much. So let's go from 33,000 ohms to 100,000 ohms. There we go. Now that's 5 volts per division. And you can see we're getting almost 10 volts from the bottom peak to the top peak. And we still have the input of 0.5. And so that's a lot more gain, but it's not exactly how the math should make it work out. So it's not a ideal op-amp. It's actually a terrible op-amp, but it's an op-amp. All right. And for what I'm hoping to use this op-amp for, this lack of precision is not actually all that important. So I'm really excited about this op-amp. It's a terrible op-amp. It's probably the worst op-amp in the world. But it's my op-amp and I love it. So for what I'm hoping to use this for, I think it's going to work really well. But I think we've gone on long enough in this one, so we'll save my ultimate goal for what I'm planning on using this for our vacuum tube computer for the next episode. So in the meantime, I'm gonna keep fiddling with this, trying to figure out all the little quirks of it, so that way when it comes time to build the next stage, I know exactly what to expect. And thank you guys so much for watching, and we'll see y'all in the next episode.